Article 250.122 at war of the National Electrical Code 2020 states that the grounding electrode conductor should have a minimum size as specified in Table 250.122. Table 250.122 doesn't specify a minimum size for 600 amp service when using a 1/0 copper conductor. Article 250.66 does not apply to grounding electrode conductors. Article 310.16 also does not apply to grounding electrode conductors. Therefore, based on the 2020 National Electrical Code, using a 1/0 copper conductor as a grounding electrode conductor for a 600 amp service is correct. Requiring a 2/0 copper conductor is incorrect. Now, considering the 1996 National Electrical Code, Article 250-91 at states that the grounding electrode conductor must have a minimum size as specified in Table 250-91A. Table 250-91 does not specify a minimum size for 600 amp service with a 1/0 copper conductor. Article 250-71 does not apply to grounding electrode conductors. Article 310-16 does not apply to grounding electrode conductors either. To clarify, the grounding electrode conductor connects the equipment grounding system or the grounded conductor to the grounding electrode. The purpose of this connection is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. Sizing the grounding electrode conductor is crucial for safety and code compliance. It ensures that in the event of a ground fault, sufficient current can flow to trip the overcurrent protection, minimizing the risk of electrical shock or fire. The National Electrical Code outlines specific requirements for sizing grounding electrode conductors based on the size of the service entrance conductors or the equivalent area for parallel conductors. Let's delve deeper into the relevant National Electrical Code articles. Firstly, Article 250.66 provides guidance on sizing the grounding electrode conductor when it connects to a grounding electrode system. This article refers to specific tables that dictate the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The service entrance conductors are the conductors that bring power from the utility company to the building's main service disconnect. Secondly, Article 250.122 addresses the sizing of equipment grounding conductors. These conductors connect the non-current carrying metal parts of electrical equipment to the grounding system, providing a path for fault current to return to the source. Table 250.122 outlines the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. Thirdly, Article 310.16, as previously mentioned, does not directly apply to sizing grounding electrode conductors. This article pertains to the allowable ampacity of insulated conductors, which is the maximum current a conductor can carry continuously under specific conditions without exceeding its temperature rating. Now, let's explore the practical application of these code sections. Imagine a scenario where a building has a 600 amp electrical service. The service entrance conductors are 500,000 circular mils copper conductors per phase. To determine the appropriate size of the grounding electrode conductor, we would refer to Table 250.66 as indicated by Article 250.66. According to this table, for service entrance conductors ranging in size from 350,000 circular mils to 600,000 circular mils copper, the minimum size of the grounding electrode conductor is 1/0 copper. This means that a 1/0 copper conductor is sufficient for grounding the electrical system in this scenario. It's important to note that the authority having jurisdiction, or OJ, plays a crucial role in enforcing the National Electrical Code. The AHA is typically a local electrical inspector or building official who is responsible for ensuring that electrical installations comply with the code requirements. While the National Electrical Code provides a set of guidelines, the AHA has the final say in interpreting and enforcing the code. Therefore, it's essential to communicate effectively with the AHA and address any concerns or questions they may have regarding the electrical installation. To summarize, the grounding electrode conductor size for a 600 amp service based on the information presented and the National Electrical Code should be a minimum of 1/0 copper when following Article 250.66 and its associated tables. Article 310.16 is not relevant for sizing grounding electrode conductors. When encountering discrepancies with the AHA interpretation, providing clear documentation and referencing the specific National Electrical Code sections is recommended. Furthermore, you could consult with a qualified electrical engineer or another electrical professional for a second opinion. In these situations, it's crucial to maintain open communication and a respectful approach to reach a mutually agreeable solution that ensures safety and code compliance. Electrical codes and standards are updated periodically to incorporate new technologies, address emerging safety concerns, and improve the overall safety and reliability of electrical systems. The National Electrical Code, for example, is typically revised every 3 years. Staying current with the latest code revisions is essential for electrical professionals and anyone involved in electrical installations. These revisions can include changes to conductor sizing requirements, grounding methods, overcurrent protection, and other critical aspects of electrical work. Keeping up to date with code changes can be achieved through various means, such as attending industry training courses, subscribing to electrical trade publications, and participating in professional organizations. The National Fire Protection Association, or NFPA, which publishes the National Electrical Code, also offers resources and training materials to help individuals stay informed about code updates. Furthermore, it's crucial to understand the specific electrical codes and regulations that apply to the jurisdiction where the electrical work is being performed. Local jurisdictions may adopt the National Electrical Code with amendments or modifications to address specific regional needs or concerns. These local amendments can vary significantly from one jurisdiction to another, so it's essential to consult with the local AHA to ensure compliance with all applicable requirements. In addition to the National Electrical Code, other relevant standards and guidelines may apply to electrical installations. These can include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, the American National Standards Institute, or ANSI, and Underwriters Laboratories, or UL. These standards address various aspects of electrical safety, performance, and testing, and compliance with these standards can enhance the overall quality and safety of electrical systems. To further clarify the concepts discussed, let's consider some additional scenarios. Suppose a service entrance conductors for a 600 amp service consist of 2 sets of 300,000 circular mils copper conductors per phase. In this case, the equivalent area of the service entrance conductors would be 600,000 circular mils, which is the sum of the areas of the individual conductors. According to Table 250.66, the minimum size of the grounding electrode conductor would still be 1/0 copper, as the equivalent area falls within the range of 350,000 circular mils to 600,000 circular mils copper. Now let's consider a scenario where the service entrance conductors are aluminum instead of copper. In this case, Table 250.66 provides separate guidelines for sizing the grounding electrode conductor based on the size of the aluminum service entrance conductors. For example, if the service entrance conductors are 750,000 circular mils aluminum, the minimum size of the grounding electrode conductor would be 2/0 copper, according to Table 250.66. It's important to carefully consult the appropriate table and use the correct conductor material to determine the minimum size of the grounding electrode conductor. Furthermore, it's crucial to ensure that the grounding electrode conductor is properly installed and connected to the grounding electrode system. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding or listed connectors. The connections must be protected from corrosion and mechanical damage to ensure the long-term integrity of the grounding system. In addition to the grounding electrode conductor, the equipment grounding conductors play a vital role in providing a safe path for fault current to return to the source. Equipment grounding conductors connect the non-current carrying metal parts of electrical equipment to the grounding system, preventing voltage from appearing on these parts in the event of a ground fault. The size of the equipment grounding conductors is determined by Table 250.122, which specifies the minimum size based on the rating of the overcurrent protective device in the circuit. For example, if a circuit is protected by a 20-amp circuit breaker, the minimum size of the equipment grounding conductor would be 12 American wire gauge copper, according to Table 250.122. In summary, understanding the National Electrical Code requirements for grounding electrode conductors and equipment grounding conductors is crucial for ensuring the safety and reliability of electrical installations. Consulting with qualified electrical professionals and staying up to date with code revisions can help ensure compliance and prevent potential electrical hazards. I'd like to elaborate on the importance of proper grounding and bonding in electrical systems. Grounding and bonding are two distinct but interconnected concepts that play a critical role in ensuring electrical safety. Grounding refers to the intentional connection of electrical circuits and equipment to the earth, providing a low impedance path for fault current to return to the source. Bonding, on the other hand, refers to the connection of non-current carrying metal parts of electrical equipment to create an electrically conductive path. The primary purpose of grounding is to limit voltage on electrical equipment and prevent electrical shock hazards. By providing a low impedance path for fault current, grounding helps ensure that overcurrent protective devices, such as circuit breakers and fuses, will operate quickly to clear a fault. This reduces the risk of electrical shock, fire, and equipment damage. Bonding, on the other hand, helps to equalize the voltage potential between different metal parts of electrical equipment. This prevents voltage differences from occurring, which can create a shock hazard if a person comes into contact with two metal parts that are at different voltage potentials. Bonding also helps to reduce electromagnetic interference, or EMI, which can disrupt the operation of sensitive electronic equipment. The National Electrical Code provides specific requirements for grounding and bonding in Article 250. This article covers various aspects of grounding and bonding, including the types of grounding systems, the methods for grounding and bonding equipment, and the requirements for grounding electrodes. It's essential to carefully follow the requirements of Article 250 to ensure that electrical systems are properly grounded and bonded. There are several types of grounding systems commonly used in electrical installations. The most common type is the solidly grounded system, in which the neutral conductor of the electrical system is directly connected to the earth. This type of system provides a low impedance path for fault current and is typically used in residential and commercial buildings. Another type of grounding system is the impedance grounded system, in which the neutral conductor is connected to the earth through a resistor or inductor. This type of system limits the amount of fault current that can flow, reducing the risk of equipment damage and voltage disturbances. Impedance grounded systems are typically used in industrial facilities and other applications where sensitive electronic equipment is present. In addition to the type of grounding system, the method for grounding and bonding equipment is also crucial. There are several methods commonly used, including the use of equipment grounding conductors, metal raceways, and bonding jumpers. Equipment grounding conductors are wires that connect the non-current carrying metal parts of electrical equipment to the grounding system. Metal raceways, such as conduit and cable trays, can also be used as equipment grounding conductors, provided they are properly installed and connected. Bonding jumpers are short lengths of wire that are used to connect different metal parts of electrical equipment together, ensuring that they are at the same voltage potential. Grounding electrodes are another critical component of grounding systems. Grounding electrodes are conductive objects that are buried in the earth and connected to the grounding system. The most common types of grounding electrodes are ground rods, metal water pipes, and concrete encased electrodes. Ground rods are typically made of copper or steel and are driven into the earth to a depth of at least 8 feet. Metal water pipes can also be used as grounding electrodes, provided they are in direct contact with the earth for at least 10 feet. Concrete encased electrodes, also known as UFA grounds, are made of bare copper wire that is encased in concrete. These electrodes are typically used in new construction and provide excellent grounding performance. In summary, proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. By following the requirements of the National Electrical Code and using appropriate grounding and bonding methods, electrical professionals can help prevent electrical shock hazards, reduce equipment damage, and improve the overall performance of electrical systems.